So once again, this is binomial, so binary. You're either orange or not orange. What are the colors? Just like orange, yellow, and brown? Are those the three colors? Okay. Independence. If we select a sample of 50 Reese's Pieces, they didn't give us independence, and it didn't say we were putting those pieces back. So that's bad, right? We would fail, but we have the 10% rule that says if our sample size is less than 10% of the population size, right? If the sample size is less than 10% of the population size, then that probability really isn't going to be changed enough to make a significant impact, right? So that's really what the 10% rule is saying. So in this case, our sample size was 50. And we were taking this out of a population of 1,000, right? Well, 10% of 1,000 is 100, and 50 is less than 10% of 100. So once again, our sample was small enough to not make a huge impact, right? That big sample, right? Or the population, right? That sample was small enough not to impact that population as much. Your set sample size. And then same probability. Well, they told us the probability of the population of orange candies was 0.4. We're kind of making an assumption that that's true, right? But hopefully that's helpful. Okay, it says draw a sample of 50 Reese's Pieces using the applet. I want you to simulate this with your calculator again. So the very first thing we need to do is declare what's our probability, and we need to represent that with numbers. So in this case, we could do 1,000 numbers, right? And we could say 1 through 400, so that would be 40%. If you get a number 1 through 400, that would be orange. And then 401 to 1,000, well, that would be not orange, right? So a lot of you really like to use the big sample size. What would be an easier way to represent 40%? What would we do, Julia? Yeah, you could just do 1 through 10. So 1 through 4 would be orange. 5 through 10 would be not orange, right? So you can do that either way, as long as somehow in your randint function, whatever numbers you choose, whatever numbers you choose, you're doing that 40% representation, right? Remember, whenever you use a calculator function, you have to label what each of these numbers represent. That's something that a lot of you lost like little half points on the cumulative test. So I want you guys to generate some samples, and remember, out of the 10 numbers that you get, you need to find the proportion of orange, right? So I'm looking for a proportion here. So if you get 10 digits, you're going to count how many of them were 400 or less, right? Yes. Just make sure to like leave it on the desk when you're done, and I'll spray it down. And then once you have your 4 things, I'm going to erase this. Put it on a dot plot. We can do sampling distributions based on proportions or x values, whatever we want, right? So if we were looking at, in this case, the proportion of orange Reese's Pieces from a sample size of 50, what we could do, right, is just cut all these values in half, and we would end up with the same distribution just with x values down here, right? Just with the number values. It wouldn't change anything about the shape, but it would change like what the mean would be, right? In this case, your mean would be a proportion of Reese's Pieces. If we were to have used the number of orange candies, the mean would have been the average number of Reese's Pieces, right? So if we were to talk about what each dot represents, well, each dot is a proportion of orange Reese's Pieces from a sample of 50, right? I put that here. And then in this case, we should also say that this is an approximation of the sampling distribution of P, right? So we talked about proportions where P is the probability that something was orange, right? That a Reese's Pieces was orange. What we also could have done was talked about X. In this case, the X they're referring to is the number of Reese's Pieces. And remember, we would actually end up with the exact same distribution, right? We would convert these all back to X's. That wouldn't change anything about the shape at all. But it would change what we're describing, right? If we were to do the mean and standard deviation for the distribution of X, the mean of the number of Reese's Pieces is sort of like, do you remember when we did the expected value? This was from chapter 6. It's sort of like the expected value where you can do n times p. And remember, you could find this on your formula sheet. This is actually on your formula sheet for binomial distributions. And then, so in this case, you'd have 50 times 0.4, which is 20 Reese's Pieces. I'm shortening that, sorry. I ran out of space. I should say orange. So we would expect to have 20 orange Reese's Pieces. And for our standard deviation of the X values, we actually had a formula for that too, right? So we would expect the typical distance from the center for the number of Reese's Pieces to be 50 times 0.4, and then probability of failure is 0.6. Oops, should be 50. And remember, these come from the binomial distributions. It's on your formula sheet, right? So in this case, we would get 3.46 Reese's Pieces, right? We could convert these to proportions really quick, right? We could just do a transformation. Remember, when you transform data, you would divide. Division actually works for mean and standard deviation. You would actually get the same values using transformations. Okay. If you look at the approximate shape of the sampling distribution, the approximate shape for the sampling distribution of X, remember, we have a mean equal to 20 for the X. That's the number of Reese's Pieces. And the standard deviation, the average distance was 3.46 Reese's Pieces, right? Maybe I'll just do ORP for orange Reese's Pieces. If you're approximating the shape, I would say it's approximately symmetric. But we can even go further that it's approximately normal because of the law of large counts. And this is where I told you these rules that we didn't really understand, didn't really apply yet, they're coming back. And we're going to keep using them over and over again. So if you really don't understand them, don't sweat it too much. We're going to keep talking about them. Okay, so if we're talking about the law of large counts, we're telling you that this distribution is approximately normal. Remember, you need to label your mean, your standard deviation of a binomial distribution. Should be centered at 20. Or if we were talking about proportions, it would be centered at 0.4, and then you would divide this number by 20 to get your proportion, right? But anyway, this is approximately normal because of the law of large counts. And if you recall, that's saying basically the number of successes and the number of failures has to be big enough, like you need to have a big enough sample of both in order for it to work. So in this case, the number of successes is n times p. That has to be greater than 10. And then the number of failures also has to be bigger than 10. Sometimes people say or equal to. It doesn't really matter. But either way, our number of successes, so 50 times 0.4, that proportion is equal to 20 successes. Well, that's greater than or equal to 10, right? In this case, our sample size times our proportion of failures is 30, which is also greater than or equal to 10. So we are good there. Once again, we were able to say normality because of law of large counts, right? And we were also able to apply the 10% rule up here in order to declare that independence. So those are some checks that we're going to keep coming back to over and over again. And I just wanted to show you guys that we can do sampling distributions with proportions, with x values, with means, right? So what I want you to do is use your samples from number 2. And in this case, we accidentally did these into the x. We did proportions already. So I want you to do the number. Since we did proportions down here, right? These were all proportions. If we were to make a dot plot of this, if we were to sketch a dot plot of this, I want your x values. You guys should be able to count those, right? So if we were to resketch this dot plot, and we already talked about this, this would look identical, right? So I could actually take, I wish I could take my camera for all those people at home. What I could do is just take this and it would be the exact same sketch, just with the number instead. So what I want you to do is just draw approximately the same picture as you see here. But if you see 0.24, well, that would mean I had 12 Reese's Pieces, right? This one would be 13, 14. This one would be 15, 16, 17, 18, 19, 20, right? Do you see how we're just doing a transformation? We're not really changing anything except for we're changing these proportions back to the x values, right? Looks like we had 22s, 23, 24, 25, no 26s, and 2 27s. So redraw that dot plot on the other page, and we're going to find the mean and standard deviation of the proportions. I know this is backwards. These x values go with the second dot plot, and the proportions go with the first. Once again, I'll have you sketch that, and then so once again, numbers 5 and 6, the distribution of x had to do with number 8, so you might want to go back and label number 5 as the mean and standard deviation that go with the graph for 8. The mean and standard deviation of the proportions, we're going to put for numbers, for number 10. So I want to show you guys how to do that one real quick too. So if we're talking about the mean and standard deviation of proportions, so all of those proportions were sample proportions. We have to find the average of all of our sample proportions. And in that case, we would expect that average proportion to be 0.4, right? We would expect it to be right in the middle at 0.4. But the standard deviation of our sample proportions, this is also going to be on your formula sheet. The formula for that, which we'll put on our big ideas, is right here. So you can see, instead of multiplying by our sample size, we're dividing by it to find proportions, right? That should sort of make sense that we're dividing by 40 because this is proportion, or 50 because this is proportions. And then you'll get your 2 answers.